I'm going to go to the practical for the conservators in this group. And I'm going to try and explain how NASA picks materials. I'm a material scientist by training, and so that's a lot of what I work on. But I'm going to start with some background on how NASA chooses its materials, and then we'll go into what the materials might be. And everything in a NASA mission, and also most military missions, flows from the mission science or the aims of the mission. So there'll be top-level requirements, and if you're landing on the moon, for instance, it might be we want to land in a certain area. That's a requirement. We want to last for 3 months. We want to survive certain temperature swings. Those are all the sorts of top-level requirements, and they're dictated by the mission. And so the materials used to build a spacecraft are always dictated by the mission science or the mission objectives. That's number one. So if you are in a museum and you have something that's going to orbit or a bit of hardware that was designed to orbit low Earth, that mission requirement for survival is going to be very different than something on the moon, which is a very high radiation environment with potentially huge temperature swings. So there'll be questions beyond that. For instance, if it's an optical-based set of instruments on the mission, then those are probably designed away from NASA by specialty groups that design optics. They got to be clean. There's no Windex in space, right? So your mission goes up clean and has to stay clean. On the other hand, if it's an RF comm mission, a lot of military missions, for instance, or communication missions, they are less clean. That doesn't mean they can be dirty, you know, but they are less clean because they just don't need to be that clean. For conservation, these things matter because it informs what kind of materials you're going to run across, because that's how the mission is designed. And the other critical factor is if it's a Class A to D mission. Class A is the highest standard. It's often human spaceflight. It's often multi-billion-dollar missions. So if it's a Class A mission, they had a lot of resources, a lot of resources. They picked radiation-hard electronics. They built in clean rooms. They tested a huge amount. They had huge amounts of environmental testing. And then there's Class D missions. Those are often CubeSats, small missions, and those have a much higher risk tolerance. And so they may pick parts that aren't rad hard. They may say, hey, we don't have that kind of money. We're only up there for 3 months or 6 months. It's not worth it. So that's another thing you can look for is, was your mission Class A, B, C, or D? I can almost guarantee that if it's human spaceflight, it's Class A by definition. So Class A through C missions are also almost always heritage parts. What does that mean? It means they've gone through a rigorous set of testing, and if possible, they've already flown. So NASA often takes parts up just to see if they'll exist. Like they'll go to the space station or International Space Station, or they'll go on a mission with a return, and they'll see how they survive. There's other testing, there's radiation testing and accelerators, et cetera. And those are flight heritage or they're flight-like tested. So they're designed for those mission environments. Let's see. I want to start by saying the only people I know, and I've worked in conservation in museums like LA County Museum and Getty, the only people I know who are more conservative than conservators are space people. And that's because the Senate runs the budget, and if you mess up, that can cost your organization money. The Congress and Senate, Congress runs the budget. If Congress thinks that you're wasting taxpayer dollars, you can't just go back to the donors. So the last thing you need to know is that an engineering unit, which is often what ends up in museums, is usually built to the same high standards as a flight unit. There's two reasons for that. The first reason is that if something breaks in the final round of testing, they go and cannibalize the engineering unit to fix it. So that engineering unit has to be built to the same high clean standards, the same radiation standards, the same thermal standards. And the second reason is, if something breaks during the mission operations, they may want to go and look at that engineering unit and try and figure out why. And they will literally take the problem part or the suspected problem out and send it to specialty labs and get it tested. Is there a reason the computer had a single event upset or multiple upsets that erase data? Is there a reason that a door isn't opening, et cetera? So oftentimes what you get is built to a pretty high standard, which is kind of cool. So now you're going to notice that my talk background changes, and that's because I'm now going to the section that is really useful for conservators, in my opinion. So optical spectrometers and gas spectrometers, they're usually kept, the design of the spacecraft is usually very specific to have low outgassing materials. That's again because there's no Windex in space. So when you go in your new car and you get that nice new car smell and your window gets all foggy and you think, oh, that's so cool, I've got a new car. Space doesn't like that. We don't want our optics all messed up with goo. Magnetometers, so if you've got something that's carrying a magnetometer, then you're pretty sure that you're not going to have a lot of magnetic materials like iron or nickel. Nickel-plated screws, big no-no. And also everything on that spacecraft, all the tools used to build it, et cetera, were degaussed. So there should be an amount of magnetic background on that particular spacecraft. Science measurements can be affected by particles. So if we're going to the moon looking for water, we don't want to carry a lot of Earth water. If we're going to Mars and we're looking for signs of life, they really don't want the people who are building that lab to leave a lot of skin cells behind, right? And furthermore, if you're really looking for signs of life on Mars, there's planetary protection. Those early spacecraft that went to Mars were baked for months, and those early spacecraft, sometimes up to 20% of the budget had to do with removing any signs of human life on the early Mars landers. So they were scrubbed, baked, and tested again and again with people taking little swabs. And if there's humans on the mission, like to the ISS, then you cannot take poisonous materials without huge amounts of special testing. So no one wants you to take up a bunch of arsenic that's going to be floating around inside the ISS. Just a side note, I have heard that the ISS is a bacteria breeding ground like a giant petri dish, and there's actually mold up there. But, but they do try and keep that down. So who's in charge of all these mitigations, we call them? Well, there's thermal engineers, there's contam control engineers, there's radiation effects, there's quality people who sort of come in and say, wow, integration and test isn't paying enough attention. There's mission assurance people who, among other things, look at GUIDEPS, which is a government-based website that lists all the parts that have failed routinely. So we don't go and buy an Intel part that everyone knows is kind of garbage, or if we have one on there, we may have to, no offense to Intel, I'm sure it's not Intel. But you know, we don't go buy a part that has shown to degrade in certain environments. There's parts, materials, and processes people on every mission who keep track of every single thing, everything that goes into a spacecraft, and usually it's on the drawings, every single thing. And there's magnetic contam people. That's just to list a few things. So in space development, there's a word called shall. And shall is a requirement indicator. So if I write up a plan and I say, as a contam control and materials person, you shall not use silicones, then anytime they use silicones, they have to either write a large amount of paperwork to explain why they use silicones, or they have to go through a review process. So there's a reason we don't like silicones. It's because they touch transfer, they creep. You ever get those silicone baking trays and notice they're always greasy feeling? It's like oil paints. It never dries unless it's super well designed, and it touch transfers and creeps, and then in radiation environments it darkens. So they've even seen thumbprints on things from silicones. But silicones can survive huge temperature swings, so sometimes there's not a lot of other choices. I will say that you almost never get tapes with silicone adhesives. They're almost always acrylic. And if you have silicone adhesives, God bless you trying to get them off. All materials, and this is a NASA standard, will meet low outgassing requirements. That is generally a total mass loss of 1%, and you can subtract water loss, and a total collected volatile materials of less than 0.1%. And there's a database, which I'll get to on that. So if you open up and find a gasket inside, and you're trying to figure out what it is, you can go look up and see if of your 3 choices, 2 of them meet the outgassing. It's going to be one of those 2 and not the other, almost always. And this goes way back. Banned materials, you are not allowed to use pure tin. Tin grows whiskers and shorts out electronics, and they get long. It's really weird. It looks like hair coming out off of the tin material in a vacuum in space, and it shorts things out. So you really aren't supposed to use that. You can't use cadmium or zinc because when they get hot in a vacuum, they sublime and they plate out elsewhere. So you will not find cadmium or zinc in your spacecraft unless there's been a really good reason. Sometimes instruments have a little bit of something like that. Magnetic materials I mentioned before. So how do we know if it's low outgassing? You're going to laugh. Outgassing.nasa.gov, open source. Outgassing.nasa.gov. And you'll see there, let's see if I can make the pointer work. Total mass loss, 0.14, 0.25, 0.52, 3.79. That guy's not going to get used. They'll use these instead. You can take the total mass loss, you can subtract. So I could say this is actually 3.71 because I can subtract that. It's still way too high. Nobody's going to use this if they can use this or this or this. It's verboten. Okay? This is an open source. Type it in right now. You'll find outgassing.nasa.gov. I will tell you, for those of you who are conservators, that Pam Hatchfield had a silicone-based sealer gasket on a bunch of her cases in Boston. And they started finding little crystalline weird things all over the artifacts inside. And what they found was that it was silicone redepositing. So this is not just for space. If you're a person who's saving materials, material culture, you may want to avoid silicones. They touch transfer, you touch your gasket, you touch your article, you got silicone on your article. And they creep, they move around and deposit on your article. That's just my opinion. I like acrylic. There are other materials. There are other materials databases. MISI, I believe you have to register for that one, and they may be a little sensitive about who gets on there. It also lists outgassing, it lists heritage. There are a whole bunch of European Space Agency things similar to outgassing and MAPTIS and MISI. Again, you may have to register for those. I can't guarantee, but usually if you're a known archivist or institution, you can get registered onto MAPTIS. And that lists all kinds of data about materials used in the past. So it's a massive knowledge base. ASTM has a bunch of space flight documents that are standards that are used across the industry worldwide. So you can always go look for ASTM stuff. They're not free, annoyingly to me, because my grandparents paid for the federal standards. They used to be mill standards, and ASTM just copied them and now charges, but yeah. I'm old, I get my grumbles. But the knowledge bases will tell you about bakeouts too. Most military, most NASA stuff that goes into museums won't have gone through final testing, so they won't have gotten baked out. But if you get things that got baked out, that'll tell you more about that. The final step after you build a spacecraft would be to take it for what we call environmental testing. And environmental testing includes shock, vibe, thermal testing, and usually electronics, magnetics testing. So your stuff may not have gone through that, but a lot of the parts will have gone through that, and so a lot of your parts will have been baked out at high temperatures. So JAXA and ESA also have their databases. You should check them. And they're often in very close alignment to the US ones because the US flies a lot of other people's instruments. Many people don't recognize this, but ESA contributed, or the British National Space, I guess, contributed to James Webb. JAXA the Japanese have often contributed instruments. I'm going to digress a little. The previous one of these conferences, I talked about how it's a large group of institutions that build these larger spacecraft. So the instruments will usually be built in different locations, sometimes NASA centers, sometimes foreign entities, sometimes universities. And then they get delivered to NASA, and NASA integrates them onto the launch vehicle, which contains usually most of the comms, up and down, contains a lot of the propulsion, et cetera. So, and they do a final testing. Yeah. So that's why all of these institutions have the same sort of requirements, because NASA doesn't want somebody showing up with a bunch of dirty stuff and going into their vacuum chambers. Guide-ups, I mentioned them previously. Guide-ups are really important. Guide-ups should be used when you get parts, because they're a national database that says which parts have regularly failed in the past, and if NASA has something that has a guide-up, they will probably remove the part because it's a known failure mechanism. And so if you have something and you're not sure what the part is, you can go back and check and see if there was a guide-up. And if you're buying a car, you might want to check and see if there's a guide-up if you can get the parts list. It's not just specific to NASA, it's everyone's. Radiation hardness, there's databases on radiation hardness. radhome.Goddard Space Flight Center, gsfc.nasa.gov. And you can look at the parts radiation listings for many things. Almost everything is built in a clean room. Even dirtier spacecraft are built in a clean room. So what that means is that you shouldn't find loose screws in there. You shouldn't find people's hair in there. You shouldn't find those fingerprints on your spacecraft. So if you're finding them, the night watchman put them on there. And that's just a heads up, but things are usually built in a clean room because they need to stay clean. Because conservators can look to flight heritage documents, you can find out what it is made of. But that's just a step. So if you can find lists of previous lunar landers, for instance, you will probably, if the parts are still available, you'll find that they're still using them. 15 years ago at Lockheed, which is a great organization, but they were still building their own boards. They weren't using integrated circuits. So you would actually find, resistors and capacitors with the fingers that you solder to down there. And you can often go back and try and find out what those are if you want to try and make something run again, just based on flight heritage, if you ask around a bit. That stuff is not as proprietary now because most people have gone to integrated circuits. And so people are more willing to talk about it. So that's it, except that I want to say everything that's done at NASA, every single thing is documented. So if you receive something from NASA and you're an archivist or an historian or a conservator, it behooves you to try and ask, can I get a parts list? Can I get a materials list? They may say no, but they may say yes. You can ask who built the instruments, because a lot of that is not, NASA doesn't put, NASA, JWST, all the instruments are by blah, blah, blah. I would go back and look who built the instruments and see if you can get some stories about your instruments. What materials were used, what kind of cleanliness, what parts were used. You may find that University of Colorado LASP will tell you. NASA might not tell you. They might not be willing to dig it up, but you may find that some of this stuff is available if you ask, but you got to ask, right? So anyway, I hope that's helpful. How am I doing for time? I'm good? Questions.